Dear students, in today's class we will see deadlock prevention and avoidance. Okay, so for a deadlock to occur, each of four necessary conditions must hold. First one is mutual exclusion. Second is hold and wait. Third one is no preemption. Fourth one is circular wait. These four conditions must hold. By assuring that at least one of these conditions cannot hold, we can prevent the occurrence of a deadline, right? So to satisfy these all four, when these all four conditions are satisfied, then only deadlock occurs. Any one of these four conditions is not satisfied, then the deadlock will not occur. So we can prevent the deadlock. We can elaborate on this, or we can describe in detail the approach by testing each of these four necessary conditions now. So mutual exclusion condition must hold for non-shareable resources. For example, a printer cannot be simultaneously shared by many number of processors. Shareable resources, in opposite to this non-shareable resources, they do not require mutually exclusive access, and therefore they cannot be involved in a deadlock. Hold and wait. To assure that hold and wait condition never occurs in the system, we must guarantee that whenever a process requests a resource, it does not hold any other resources. So one protocol that can be used requires each process to request and it is be allocated all its resources before begins the execution. One more alternative protocol is there. I repeat, the first protocol is used, can be used, requires each process to request and it will be allocated all its resources before it begins its execution. Second alternative protocol is it allows a process to request resources only when it has a none. Okay. A process may request some resources and use them. Before it can request any additional resources, it must release all the resources that is currently allocated. Okay. So to illustrate the difference between these two protocols, we consider a process that copies the data from DVD drive to a file on a disk. Okay, so sorts the file and then prints the results to a printer. So if all these resources must be requested at the beginning of every process, then the process must initially request the DVD drive, disk file and printer. It needs three resources: DVD drive, disk file and printer. So it will hold the printer for its entire execution, even though it needs the printer only at the end. So second method allows the process to request initially only the DVD drive and disk file. It copies the DVD drive to the disk file and then releases both the DVD drive and disk file. The process must then again request the disk file and the printer. So after copying the disk file to the printer, it releases these two resources and terminates. Okay. So both of these protocols have two main disadvantages. The first disadvantage is resource utilization may be low because the resources may be allocated but unused for a long period. Second disadvantage is starvation is possible. A process that needs several process popular resources may have to wait indefinitely because at least one of these resources that it needs is always allocated to some other process. Third one is no preemption. Okay. No preemption. The third necessary condition for deadlocks is that there be no preemption of resources that have already been allocated. To ensure that this condition does not hold, we can use the following protocol. The protocol is if a process is holding some resources and request another resource that can not be immediately allocated to it, then all resources the process is currently holding are preempted. So it means that these resources are implicitly released. The preempted resources are added to the list of resources for which this process is waiting. The process will be again restarted only when it can again gets its old resources as well as the new ones that it is requesting. Okay, so fourth one is circular wait. The fourth and final condition for deadlocks is a circular wait condition. So one method to assure that this condition never holds is to put a restriction on a total ordering of these all resource types, and to require that each process requests resources in an increasing order of enumeration. See, next is deadlock avoidance. Deadlock prevention algorithms prevent deadlocks by restraining how request can be made, but the restraints ensure that at least one of these necessary conditions for deadlock cannot occur, and hence that a deadlock cannot hold. But possible side effects of preventing deadlocks by this method, however, are low device utilization and reduced system throughput. So first is a safe state. If safe state is safe, a state is safe if the system can allocate resources to each process up to its maximum in some order and still avoid a deadlock. So usually a system is in a safe state only if there exists a safe sequence. A sequence of processes P1, P2, P3 up to Pn is a safe sequence for the current allocation state. If for each process pi that resource request that process pi can still make that can still make that satisfied by the currently available resources plus the resources held by all processes pj. So with j is less than I, the safe state is not a deadlocked state. Okay. So now we will see Banker's algorithm, very interesting algorithm. The name was chosen as a Banker's algorithm because the algorithm could be used in a banking system to assure that the bank never allocates its available cash in a such a way that that it could no longer satisfy the needs of all its customers. So usually banks contain or it has some cash or amount. It does not give the entire amount or cash to only one customer, so that they can satisfy all the customers of its bank. Similarly, the same concept is used here also. When a new process enters the system, it must declare the maximum number of instances of each resource types that it may need, and this number may not exceed the total number of resources in the system. So when a user requests a set of resources, the system must determine or find out whether that allocation of these resources will leave the system in a safe state or not. So if it will leave it in a safe state, then the resources are allocated, otherwise the process must wait until some other process releases sufficient resources. So many amount of data or several data structures must be maintained to implement this Banker's algorithm. These data structures encode the state of the resource allocation system. So we need the following data structures, where n is the number of processes in the system and m is the number of resource types. So available, a vector of length m indicates the number of available resources of each type, and if a available of j equals to k, then k instances of resource type ri are available. So maximum, that n into m matrix defines the maximum demand of each process, and if m max of ij is equal to k, then process pi may request at least at most or maximum k instances of resource type ri. Allocation, and n into m matrix defines the number of resources of each type currently allocated to each process. If allocation of ij equals to k, then process pi is currently allocated k instances of resource type rj. Need, an n into m matrix indicates the remaining resource need of each process, and if need of ij equals to k, then that process pi will need k more instances of resource type ri to complete its assigned task. uh, we have to note here that is the need of ij equals to maximum of ij minus allocation of ij. In next class we will see deadlock detection.